My name is Pierre Rocca. I'm a PhD student at the University of Bordeaux. And in today's presentation, we're gonna see whether the current French mobile network can support the deployment of agricultural robots. For a bit of context, agriculture negatively affects planetary boundaries and vice versa. And what is at stake is possibly the difficulty to provide a sustainable food production in the long term. So for a public institution like the European Union, one lever is to promote digital agriculture, which is the fact of using ICT to optimize and monitor agricultural processes. Digital agriculture encompasses a lot of different technology, but here we will mainly focus on robots. And more specifically, I will talk about robots that are able to do as autonomous electric machines that are able to do seeding and weeding. It's rather an emerging technology than fully mature and commercial product, but it comes with few promises, such as increasing the production both qualitatively and quantitatively, while reducing input uses. But it also comes with identified risks, such as increasing the environmental impact due to deploying more ICT in agricultural fields, or locking in the sustainability to one path. And a more social problem would be the increased dependencies of farmers to manufacturers. Okay. So regarding previous work, they mainly focus on the impact of the robots themselves. You have few comparative LCAs, and more recently a parametric model regarding large-scale deployment of robots in French rural crops. But the network use of those robots is constantly overlooked. So that's why we try to research this subject. Because we see that robots need online services to work. And some of those online services require to transfer a lot of data. For the identified services that we will use as tested scenario in this study, we will consider the RTK position correction that help to improve the accuracy of robots, which is a very low demanding service in terms of data transmission over the network. Then we will consider video streaming to remotely control the robot. And finally, we will consider edge computing, which centralizes calculations on edge servers. This last scenario is a really prospective one, but it could come with different benefits, such as increasing the robot autonomy and centralizing data and making it easier for manufacturers to manage equipment and algorithm updates. And the question behind this paper is what impact would a large-scale deployment of robots have on the mobile network usage? To do so, we will follow a consequential approach to first answer this question on the existing network infrastructure, and then on additional equipment that are needed to improve the capacity of robot to manage agricultural area. So, okay. So as we said, as we will talk about mobile network, our study rely on an underlying mobile network model, which define the mobile network as a set of sites spread across a territory. A site is composed of a support, you see here, yeah, it's okay, and also several antennas that are oriented according to sectors. Each sector will be composed of different cells, and a cell corresponds to the transmission area of a certain frequency band. And a frequency band is associated with a certain kind of technology. For example, it could be 4G or 5G. A data transmission capacity that we call here the spectral efficiency, a range radius, as well as a certain bandwidth. And in our model, we will consider three groups of overlapping frequency bands. The low one in yellow here, the lower mid one in orange. Both are related to the 4G technology. And finally, we will consider upper mid frequency band that relates to 5G, 3.5 gigahertz. Now that we have a clearer picture of the robots and the network model that underlie your study, it's time to describe the overall methodology for studying the impact of the robots deployment on the network usage. To do so, we will follow 3 main steps, and each of these steps has a related question. The first step is to determine what agricultural area, that I will later call UAA, is covered by the mobile network. Then we will try to estimate what percentage of this agricultural area is actually manageable by robots. And finally, what is the carbon footprint that relates to the network used by deployed robots. So the first step consists in estimating what agricultural area is covered by the mobile network. And to do so, we will take 2 inputs. The first one is a map of all French agricultural parcels dedicated to cereal and vegetables. And we will also consider a database from the French National Agency of Radio Frequencies that contain existing mobile network sites, their geographical position, and technical information, such as the cells that are used on each site. These inputs are matched together to determine what agricultural area is covered by the internet, and this for which frequency. In this zoomed local example, you can see first in dark gray the agricultural area that is not covered by the mobile network. Then in color, the agricultural area that is covered by a certain frequency band. In yellow, you will have the agricultural area covered by low, which represents approximately 83% of the total national parcels that are covered by this kind of frequency. Then you will have lower mid in orange that's stacked over low, and finally upper mid that's stacked over the lower mid in red here. The next step of the method will consist in simulating a deployment of robots on covered agricultural areas while taking into account the local limits of the mobile network. To do so, we will first only consider the network that exists, so as given by the INFR database. So let us consider here a certain sector, in the hexagonal shape, that covers an agricultural parcel, the gray square. The sector covers a certain part of the agricultural area, the dashed one here, and also can handle a certain data volume. Okay. On the other hand, we have a robot that is able to manage a certain area and uploads a certain data volume. Ideally, the number of robots we would like to deploy, the number of required robots, is the one that deploy enough robots to fully manage this agricultural area. However, as the sector can handle only a certain fixed data volume, the number of supported robots by this network can potentially limit the number of deployed robots. So that's why we have here a part of the covered area that is manageable in green and a part of non-manageable area while it's covered, because robots that can be supported by the network only cover a certain fraction of this area. Finally, the percentage of manageable area here is the number of deployed robots over the number of required ones. Is it clear for the moment? So in the second time, we will try to upgrade the network, only considering existing mobile network sites, for example, by adding cells, in order to increase the capacity of the network to deploy more robots and to improve the part of manageable area, reducing the part of non-manageable one. Okay. Next, so we will assess an inventory of the used network equipment based on the shift project methodology that gives us a carbon footprint estimation of the embodied emissions, considering extraction and manufacturing of the used network equipment. We do not consider the robots here, but only the network equipment that are used by the robots. We will also account for the energy consumption by distinguishing the static energy consumption, that is the one required to keep the network equipment switched on, and the dynamic one that will depend on the data load that are transferred by the deployed robots over the network. A quick reminder of the 3 scenarios we consider, and then we will talk about the results. Each scenario corresponds to a same type of robot model, so the same capacity in hectare, but relying on different online services. And for a given scenario, we will deploy all the robots using the same service. So we first have the RTK correction that is really low data demanding, then the stream one, and finally the edge computing one. Okay. So now let's talk about our results. Overall, we observe that for a fixed number of sites, the more data intensive a scenario is, the less it can manage agricultural area, the more it uses cells while relying on higher frequencies, and the more the upgrade of the network require additional cells. Furthermore, we remark that between the scenarios, we have really varying impact depending on the data intensiveness. The first result we can express is the part of manageable agricultural area. So in purple, only for the existing network, and in a clearer color, the additional manageable agricultural area with upgrade of the network, so by adding cells notably. What we see here is for the RTK scenario, you can fully deploy all the robots to cover the 83% of agricultural area that is covered by the mobile network without upgrading the network. On the other hand, you see that for the edge scenario, even by upgrading the network, you cannot manage 40% of the total agricultural area with the robots. A complementary result is to express the deployment of robots as used cells. So on the left panel here, you have the amount of cells that exist on the network covering agricultural area for each frequency band. And on the right panel, you will have the number of cells that are used by each other scenario. So for the ATK1, we only use the low cells, which is consistent with the first results. And what we see, there was a problem with the export of the PDF. So the colors are not really, but here is the additional number of cells for the upgraded network for the corresponding cells. So here we see that for the edge, first, only on the existing network, sectors with only low cell cannot deploy alone the edge scenarios, as the robots using edge are too data demanding for cells for sectors with low cells only. And for the upgraded network, we see that the total amount of upper mid frequency band, upper mid cells that are added is higher than the one initially existing on the network. And finally, we will express the impact as additional greenhouse gas emission and energy consumption compared to the initial network. As we are in a consequential approach, the results on the left should be added to those of the existing network. And we distinguish between manufacturing in dark blue, then static consumption, and then dynamic consumption. And what we see is that for the RTK, there is no additional impact, as we do not add more cells than those existing on the initial network, and the dynamic energy consumption of this scenario is negligible. But for the edge one, we will add approximately half more carbon footprint than already existing on the network. So, okay. Now we can do a comparison of this use of network by the robots and the deployed robot themselves. To do so, we adapt a former study that we done that was only focused on agricultural robots themselves and not considering the use of the network. And we adapt the parameter to keep the same surfaces, the same passes, and the same workload. We have to keep in mind here that there is not a same number of robots between the stream and the edge scenarios, as the stream one manage way more agricultural area than the edge one. And what we see is that regarding energy consumption, the energy to the network used by deployed robots account for around 20% of the one of the deployed robots. And for the edge scenario, the energy consumption of the usage of the network by the deployed robots is nearly 2 times more than the one of the deployed robots themselves, which clearly encourage the fact that to consider the network when assessing the environmental impact of deploying robots for agriculture. And for the total manufacturing greenhouse gas emission, results for the use network are way less significant compared to those of the deployed robots, but it's also because we are in a consequential approach. So the use network only accounts for additional equipment that are due to existing site upgrades. So we do not account, for example, for already deployed site here. If we were allowing ourselves to add more sites, we should account them in the impact of the use network. So those results could be quite different regarding the manufacturing greenhouse gas emissions. Okay. Finally, here we try to do a per hectare relative comparison between scenarios, because as they do not manage the same percentage of UAI, it's not really, we cannot really see the huge difference between them. So what we see here is that we divide the number of cells per the amount of hectare that is managed by the deployed robot. What we see, for example, here is that using edge instead of stream needs to multiply by 3 the number of used cells for the scenario. And regarding additional carbon footprint, choosing edge instead of stream multiply by 9 the amount of additional carbon footprint. Oops, sorry. So to conclude, we presented a consequential model representing the use of a mobile network by a deployment of robots. And what we see is that the more intensive a scenario is, the less it can manage agricultural area, the more its additional impact are important, which clearly question for those most intensive scenarios, their territorial feasibility and their environmental relevance. Sorry. And finally, as perspective, we would like to allow the addition of more network size to compare scenarios on a fixed manageable area. We would like to compare different territories, for example, in terms of parcels distribution, take over distribution than the one of France, and also consider non-flat agricultural area that could, or network model would be less optimistic with that. So here, currently, we are quite conservative. And finally, it would be interesting to extend the perimeter to also account for the robots, but also the robot charging station. And for example, for the edge scenario, the additional data center uses. Thanks for your attention. If you have any question,